So we are online now, you can start.
Okay, so good afternoon to everyone. So maybe we can, of course, wait a few seconds so that various people can join. Okay, so I think we can start, and good afternoon to everyone, and welcome to our monthly meeting for the colloquia at the Astrophysics, at the Physics and Astronomy Department of Padova. Today we have the pleasure to host, even though only virtually, Professor Eiichiro Komatsu from the Max Planck Institute for Astrophysics in Garkin. Let me spend a few words to introduce him, especially for the young students. Professor Komatsu got his PhD in 2001 at Tohoku University in Japan, actually in collaboration also with Princeton University. After his PhD, he moved to Princeton University for a postdoctoral position. And after that, he moved to the University of Texas at Austin, where he became a professor, and actually where he was the director of the Texas Center for Cosmology until 2012. In that year, he actually moved to Garkin, where he became, and where actually he is at present a director at the Max Planck Institute for Astrophysics. Professor Komatsu actually is an internationally renowned cosmologist. He gave different crucial contributions in cosmology and also in astrophysics. Let me in particular remind his various achievements regarding the study of the cosmic and microwave background, in particular, for example, to investigate the initial conditions of the universe, which will be actually the topic of this colloquium today. And he has been and he is at present a member of various international collaborations from galaxy surveys. For example, he is co-leading a galaxy survey with the prime focus spectrograph on the Subaru telescope. And in particular, he also devoted much of his effort to as I mentioned, to the study and to the analysis of cosmic microwave background anisotropist data. He was a member of the WMAP team. He is at present a member of the satellite Lightbird, whose main aim actually is to measure with exquisite precision the polarization of the cosmic microwave background photons. Actually, thanks to his various achievements, he received many prizes and honors. Just let me mention a few. The list, of course, is incomplete. In 2012, he received the Gruber Cosmology Prize for the work that he did within the WMAP team for cosmic microwave background studies. In 2015, he got the Astronomical Society of Japan Hayashi Prize. And in 2018, he got the Breakthrough Prize in Fundamental Physics with the WMAP team. Recently, in 2020, he also got the Van der Waals Professional Chair at the University of Amsterdam. So I would like to welcome Professor Komatsu. It is really a great pleasure to have him here. Unfortunately, we can just do this kind of colloquium online, but of course we will be very pleased to have Professor Komatsu in person here, probably, let's hope, next year. And so today we'll tell us about a very fascinating topic, finding gravitational waves from the early universe. Thank you. I think you can start.
Ok, grazie Nicola. Per la introduzione. the pointer. Yeah, pointer. Ok. Buonasera a tutti, grazie per aver partecipato. I'm very excited to tell you about finding gravitational waves from the early universe. So let's begin now. Last month, I hope you still remember, and you haven't seen it yet, please go to this YouTube site to watch really beautiful colloquium by Professor Barry Barish. And it's perfect because your memory, I hope, is still fresh. And he started by describing to you various sources of gravitational waves. And then he actually had the topic of today's colloquium already, although he was kind enough not to talk too much about it, except he said, signals from the early universe, that may be the most profound of all. Yeah. So you go to 16 minutes. So this 961 seconds here, right? You can hear that. And he even has a map of the cosmic microwave background. This will be the subject of today's colloquium. So he really nicely first introduced to you concepts of gravitational wave that I can just follow up. And I will now tell you about a primordial gravitational wave from the early universe. Now, Professor Barish would use the direct detection methods. I'm going to use the cosmic microwave background, which is the photons, and in particular, polarized parts of the photon coming from the early universe. So in other words, we look for the signature of gravitational waves in the polarization of the fossil light of the fireball universe, instead of looking at gravitational wave itself. So let's try to look at our sky from visible to infrared to submillimeter to microwave. Now, what you're looking at is our place inside the Milky Way. And when you look up the sky, it's a full sky. Let's try to plot everything on the screen. So you're looking now at the whole sky. Then you go to longer wavelengths, near infrared, far infrared, some millimeter. By the time you go to microwave, the sky is filled with light from the Big Bang. And then you start improving the contrast of your image by making better and better instruments. You start seeing fluctuations here, right? So this in the middle is the light coming from our Milky Way. But outside of that is the light coming from the very early universe. Now, what you see on the top right rotating is the Wilkinson microwave anisotropy probe satellite that we use to make this measurement. So this, what you see here is the measurement we made. And if you want, I even have a beach ball here that will tell you where, at what location in the sky, what is the temperature. And the contrast here is only 1 part in 100,000. So it's pretty tiny fluctuations. That's our topic. But often the explaining the cosmic microwave background and saying that it's a light coming from the fireball universe, this is just too much sometimes, especially for public audience. So to that end, and of course I have to say, I don't have to remind you that scientists, okay, we are professional doing science, but we are often terrible communicating our discovery to the world. So then I was scratching myself, scratching my head. How can we make this situation better and realize the best way is to, first, we communicate with professional science communicators. Then we ask science communicators to create the contents that they can then talk to the public because they know what's best to reach out to the heart of the public audience. Scientists think too much about the brain, but they know, how to really penetrate into the heart of the audience. So we created the movie, Horizon, teaming up with movie director Hiromitsu Kosaka. He's a world-renowned movie director, especially for full dome theater. So it's a planetarium dome movie. And I will show you, so if you go to the YouTube and then search for Horizon Edge of the Visible Universe, you see the trailer. Unfortunately, the whole movie is not available yet online, but I will show you a bit of it. And because it's a full dome, you see the circle, and you have to imagine that center of the circle is above your head, right? So that would be the top of the dome, and the front, so bottom will be in front of you, top of the circle is behind you, sides are sides. So let's begin.
The cosmic background radiation was predicted as a consequence of the expansion of the universe.
The beginning of the universe was like a dense ball of fire. Everything was immersed in light. It was just like the center of the sun, like a fog where light couldn't travel straight. However, when the universe cooled down due to expansion, the fog cleared and light could travel farther. Shouldn't this light reach the Earth today?
This light gives us the oldest picture of the universe that we can ever see directly.
But the wavelength of this light has been stretched by the expansion of the universe, and it has gone past visible light and turned into microwaves. Microwaves that come from every direction at once. That's the evidence for the expansion of the universe.
So this makes our life so much easier. And I don't have to say anything. I just show this movie and the people get it. Well, I hope at least they get it. So this light, right, very old light that comes from all the directions. And so let's really dig deeper in there, understanding where they actually came from. So light, you know, if we have light here, they just propagate outward and they're gone. So universe could not have been born in a single point, therefore, entire universe had to be lit up like this. Now, if you had a light that's only 1 light year away, they come and go in 1 year. So clearly that's not what we are observing. The light we're observing today came very, very far, so far away, amazingly so far away. And they traveled 13.8 billion years to finally reach us, okay? So we're really looking at super far away light, super old. Because the speed of light is finite, so we now see far away. But because the light has a finite propagation speed, as you go farther, the younger the universe would look. So you see younger and younger light here. And then this is our world, okay? So this is where this light was originated. And they travel so far away to come to us. So one thing that's important, the universe was hot and dense before, and photons were scattered by electrons very much until universe cooled down to about 3000 Kelvin. This moment, when universe became transparent, is so-called the surface of last scattering. This is the moment when electrons last scattered photons. Now, it's the key, okay? Scattering of photons would generate polarization. So polarization of photon was generated right there when photons are last scattered by electrons 13.8 billion years ago. But then you ask, wait a minute, then that's the end, right? We can never reach the early universe beyond this period. This is the period when universe was 3000 Kelvin. It's about 400,000 years after the beginning of the universe. Is that it? It's the only thing we can see. How can we see beyond this wall? And we don't use imagination. We use sometimes imagination, but we use laws of physics. Huh? And then, so before we talk about gravitational waves, let's talk about the sound wave, because that's the currently the impressive achievements that researchers have made, and we call this scalar mode, right? So density waves, sound waves, scalar modes. So laws of physics. What we use is a gravitational field equations, Einstein's equations, or Poisson equation in the Newtonian limit, and the energy conservation of photon fluids, energy conservation of atoms, baryonic fluid under gravitational potential, and the momentum conservation, so velocities of all components, photons, and also the baryons under gravitational potential, and they're tightly coupled by Thomson scattering. You don't have to know what they are, but just I want to tell you that we are not doing anything complicated. We're just solving Einstein's equations coupled to energy and momentum conservations. More correctly, we're solving Boltzmann equations coupled to Einstein's equation. Then we just let it evolve.
The cosmic background radiation is the wall at the edge of the visible universe. We cannot see directly the further past beyond this wall. But these temperature fluctuations may tell us what happened in the further past.
The conditions beyond the wall of the cosmic background radiation could be thought of as a liquid with high temperature and high density. You could say it was like a hot soup. Something happened behind this wall that made waves, which can be seen in the fluctuations in the cosmic background radiation. There must have been a grand sound that shook the universe. We can learn a great deal about the universe if we can extract this cosmic sound. The origin of the sound would be the moment of the birth of the universe.
Basically, at the beginning of the universe, we make some impact, which will be our initial condition, perturbation. We solve Einstein's equations and Boltzmann equations, energy conservation, momentum conservation, to let it evolve toward the surface of luster scattering. Then we compare that to observations to learn about, for example, the composition of the cosmic soup. Now, if you know what this is, right, it's miso soup. So universe, when it was hotter than 3000 Kelvin, was just like miso soup. I hope you know what that is. It's like a zuppa di miso cosmica. When the matter and radiation were hotter than 3000 Kelvin, matter was completely ionized. It's in a plasma state, which would behave just like a fluid soup. Then you throw, tofu's into miso soup and watch how waves propagate. And if you change the composition of miso, the ways that the waves will propagate would be different. And depending upon how, you observe the patterns of these waves, hoping that you could learn about the composition of the soup, composition of the universe. So that's what we do, yeah? And to analyze this wave, we use the power spectrum. So we basically take these temperature anisotropies and decompose them into cosine and sines. Well, because we're dealing with a spherical sphere, we actually decompose them into spherical harmonics. They make a diagram showing the strength of each wavelength as a function of the wavelengths. Well, actually, it's a momentum, so it's 1 over wavelengths, like that. So the y-axis is the amplitude of waves of a given wavelength. And x-axis is 1 over wavelengths. So as you go to the right, it's shorter wavelength. As you go to the left, it's longer wavelengths. And you see this oscillation, which proves that the universe was just like zuppa de miso before. Yeah. So let's dig deeper in there. So you start out with this map, then you decompose them into spherical harmonics. Yeah. And then if you go to the very left, that's wavelengths as big as the whole sky. And as you go to the right, you start seeing shorter and shorter wavelengths, higher and higher spherical harmonics, multiples, L. Then by the time you're done, right? And then of course, when you recombine everything together, you get the original map back. So it's nothing but Fourier analysis. So this proves that the universe was once in the Dzupadi-Miso state. And this was predicted in 1970. So Jim Peebles and his very first graduate student, Yu, solved Boltzmann equations coupled to Einstein's equation to predict that there would be sound waves. This was 1970. Then sound wave was finally discovered 30 years later. Okay, so sometimes basic science, theoretical physics takes that much time to be confirmed. And of course, you heard beautiful talk by Professor Barish 1 month ago. In that case, detection of gravitational wave took 100 years after the Einstein's prediction. We have to be patient and maybe healthy also, to see the discovery like that. And then let me also, so how does he look? Actually, this drawing is pretty good. So he looks like just like that. So this was a conference. When conference still existed in real life, it's a conference in Goa, India. It's a resort place, and we're just enjoying sunshine together. Seems like, century ago. Now, in the meantime, in Moscow, former Soviet Union, Rashid Sunyaev and Yakov Zerdovich did exactly the same thing. So they also predicted in 1970, the sound waves would be present. Yeah. So then these predictions became, so these predictions were confirmed. Really amazing. It's really the triumph of theoretical physics. What if somebody told you that the early universe was like, in this case, maybe, borscht, or in Italian, like zuppa di pomodoro, or, minestrone. Somebody told you that the universe was like a soup, right? What would you say? These are really bold predictions that will be confirmed 30 years later. That's really beautiful.
We can use a computer calculation to recreate the state of the universe this sound traveled through. The universe at this time was dense and behaved like liquid, such as a soup. Ingredients of the soup are the same as those in today's universe. Matter that makes stars and galaxies. And dark matter and dark energy exist, even though they cannot be seen directly by our eyes. Galaxies can keep their shapes thanks to dark matter providing gravity. It's thought that the universe's expansion is gradually speeding up due to some dark energy pushing space apart. These are the three main ingredients of the soup. Space expanded with time. Let's give some impact to the beginning of this model. Great. I have a pattern for the cosmic background radiation. The reason that this particular pattern does not match our observations is because the ratio of ingredients in the soup is wrong. Waves do not travel through in a thick soup like they do in a thin soup. I'll use the power spectrum to make the patterns match. I have to adjust the ingredients to make my calculation agree with the data. Incredible! The visible part of the universe, like stars and galaxies, makes only 5%. The universe is dominated by invisible components.
So that's very exciting, interesting that we have dark matter, dark energy. We don't know what they are, but that's not the topic of today's colloquium. Today's colloquium is rather who gave this initial impact. Let's give some impact to the beginning of this model. And once you give the impact, we solve Einstein's equations and Boltzmann equations to let it evolve. And we predict power spectrum to which we compare our data and learn something about it. But if there was no initial impact, nothing would ever happen. No sound waves, nothing, no zipper, nothing for you. Who gave the initial fluctuation? The leading idea is nobody gave the initial fluctuation. Initial fluctuation quantum mechanically emerged. And somehow these quantum mechanical fluctuations became macroscopic, because we all know that quantum fluctuations can exist in microscopic world all the time, but they don't become relevant on large scales. So somehow something happened in the early universe that connected these microscopic fluctuations to macroscopic fluctuations. So essentially, our current paradigm of cosmology tells us gravity and quantum, and when you merge them together, this explains all the structures that we see in the universe: galaxies, stars, planets, and eventually life on those planets, right? So the reason why you're listening to my colloquium today, and I'm giving you a colloquium today, is because of this, okay? Something happened in the early universe. So this missing link between micro and macro is the cosmic inflation. In the early universe, you have quantum fluctuations on small scales that are then stretched by enormous exponential expansion of space called inflation. And this suddenly, this microscopic fluctuation become macroscopic fluctuation. So let's understand this. Let's imagine that distance between 2 points in space is stretched in proportion to A. A is a function of time. It's just telling you how much expansion took place. If the universe became a factor of two bigger relative to some arbitrary time, A is 2. Then I take the time derivative of that, so I get A dot. So that has a dimension of 1 over time. I also divide A dot by A. So I get like a E folding time of that expansion. That's called Hubble expansion rate. It's A dot over A. Still has a dimension of 1 over time. If I solve the A dot over A equal H, I can formally solve it, integrate it. Then I get A, that's E to the HT, integrated. Then during inflation, A increases exponentially. So that means H has to be roughly a constant. So if A is exactly constant, H is exactly constant, scale factor is exponential. In this Corona time, everybody understands the exponential, okay? So when I give this talk to the public, I don't have to explain what the exponential anymore. Maybe that's the only thing that, only good thing that we all learn from the pandemic. Now everybody knows what the exponential is. However, inflation has to end, because otherwise it leaves universe completely empty. This means that H has to be a slowly decreasing function of time. That's a prediction. How do we test that? So now I ask quantum part of it, okay? It's really actually the merger of gravity and quantum. So during inflation, fluctuations are constantly produced over time. Then you ask Heisenberg, Okay. What if I have some time? Then I wanted to calculate what the quantum mechanical fluctuation I can have. The answer is, if you promise to return to the vacuum, the energy you borrow, you can borrow a lot of energy, okay, in short time period. So the energy you can borrow is inversely proportional to the time you borrow. And during inflation, that time you borrow inverse is h. So the quantum fluctuation you can borrow from vacuum is proportional to the Hubble expansion rate. Now here's the key. At some time, fluctuations are produced in proportion to h and then stretched. And we observe it some wavelengths. Sometime later, okay, another fluctuation was produced. Amplitude was proportional to h at that time, which is less than before. But because this fluctuation was produced later, there was less time to be stretched. Therefore, this wavelength will be shorter than the one before. So if I see 10-degree fluctuations in the sky, that must have been produced earlier than 1-degree wavelength fluctuation. That amplitude should be smaller than that 10-degree because h has to be decreasing over time. So 10-degree fluctuation amplitude should be slightly larger than 1-degree wavelength fluctuation, and that in turn is slightly larger than 0.1-degree wavelength fluctuation, and so on. So all we have to do is to measure the amplitude of fluctuations as a function of wavelengths, and I will tell you how h changed over time. But if you look at actual data, it looks, maybe slightly decreasing, but then boom, and gone, decrease up and down, up and down. So what's going on? Of course, what's going on is the physics of miso soup, which you can now remove because we understand the physics of miso soup now. And this is the power spectrum of the primordial quantum mechanical spectrum of fluctuations. In this case, it's constant across all wavelengths. Inflation never ends. So maybe you have more fluctuation on small scale than larger scale, or more fluctuation on larger scale than small scale. So let's parameterize this as a power law. The amplitude of waves is proportional to the L to ns minus 1 power. Ns is 1 is exactly equal, so that's not what we want. Ns less than 1 would predict this correct shape. So let's measure Ns. I want Ns to be less than 1, okay? COBE satellite measured Ns to be roughly 1, but error bar was too big to tell whether it's less than 1. And COBE didn't really have antenna, didn't really have a telescope to focus light. So the angular resolution was limited to very, very large scales. WMAP, we had 2 real telescopes, parabola antennas that can focus light better. The diameter of the telescope was 1.5 meter. So we could focus light better and we could get, oh, okay, interesting. NS is less than 1. But 2 point something sigma. So we couldn't really claim the discovery by ourselves. But then we realized, hold on, if we wanted to measure small scale things, we don't really have to launch the satellite. Maybe we can rely on other experiments, taking data from Chile, where you can build a 6-meter telescope, or Southpaw telescope, 10-meter. Southpaw telescope was led by University of Chicago. The Komatsu telescope was led by Princeton University. So we could, though they have these beautiful, beautiful measurements, we could combine our data sets and their data sets to have a bigger lever arm, because NS is the tilt. Then we could get 3.5 sigma evidence for NS less than 1. Most cosmologists would be very happy and declare the victory. But because we're talking about here, things like all the cosmic structures, including ourselves, came from quantum mechanical fluctuation. We wanted to have a better significance, but then we couldn't do it with CMB data alone. So we had to use external data sets such as distribution of galaxies then claimed a 5 sigma discovery of NS less than 1. That was year 2012. We're very excited, but at the same time, is this really, are we really sure? We're combining two different data sets, so maybe it would be better to do it all with CMB. A few months later, Planck satellite, so this is a European Space Agency satellite. Professor Bartolo was a key player there, as well as the Professor Matarese as well. So Padova played a big role. You should congratulate them really big next time you see them. So they, using a Planck data and our data combined, for the first time, detected NS less than 1, more than 5 sigma, using CMB datasets alone. So year 2012, year 2013 was a very special moment for cosmology. We really celebrated. Maybe it's true that all the structures we see in the universe came from quantum mechanical fluctuation. Can we do better than that? Okay, so quantum mechanical fluctuations on the ground state. So the previous result is NS, right? We're using Heisenberg's uncertainty principle. That's pretty quantum, yeah? I mean, that's it gotta be quantum effect, but there's another way that you can look at this. That's a distribution function. So wavelengths, wave function of quantum mechanical fluctuations in ground state, 0-point vacuum energy, is a Gaussian. Do we see that Gaussian distribution? So x-axis is the temperature values, y-axis is the number of pixels having that temperature. And ta-da, the answer is yes. Okay, so these CMB fluctuations have NS less than 1 as predicted by inflation, Gaussian as required for quantum mechanical 0-point fluctuations. And there are a couple of things that I didn't tell you because we don't have time. These are also checked, adiabatic super horizon fluctuations. Then, maybe we can just stop here and congratulate, okay? Oh, so okay, we all came from quantum mechanical fluctuation. Write them into the text, and kids, tell you, oh, dad, mom, did you know that we all came from quantum mechanical fluctuations? And they will ask you, where did the quantum mechanical fluctuation come from? And you say, you go to the university and study yourself. We could do that, but we don't stop. We want more evidence. Inflation produces quantum mechanically, not only density fluctuations, but also gravitational waves. We haven't seen it yet. We want that. Why? Because, as Carl Sagan said, extraordinary claim requires extraordinary evidence. So let's talk about gravitational waves. So gravitational waves, you heard a beautiful introduction by Professor Barish 1 month ago. Let me just remind you, it's a spin 2 nature of gravitational wave that will give you these 2 polarization states. When you sprinkle particles in a ring form, then distance between 2 particles change anisotropically in this manner. In this case, gravitational waves are coming toward you. Okay, so I have x-axis, y-axis, and gravitational waves are propagating in z direction, coming toward you. Then, I can just calculate the distance between 2 points. So Cartesian coordinates. If the universe isn't expanding, the s squared distance is dx squared plus dy squared plus dz squared. When universe expands in proportion to scale factor a, distance squared between 2 points is proportional to a squared. Then I can write this into slightly more fancy form using Kronecker's delta. This is exactly the same as before, it's just fancier way. Then I introduce distortion in space. So space is no longer Euclidean. This is a non-Euclidean geometry. And this Hij is a distortion in space. It's a 3x3 symmetric matrix. This has 6 components. And then we demand that the gravitational waves are transverse. So when you multiply Hij components by the direction vector of wave k, then k and Hij should be orthogonal to each other. So that will give you 3 conditions for HIJ. I also demand that this distortion does not change volume. It does not change density. That these are tensor modes, not scalar mode. That requirement is that HIJ is a traceless. So it does not change the area of this ring, okay? That will give you 1 condition for HIJ. We have 6 components. We have 4 conditions. 6 minus 4 is 2. So that's 2 physical degrees of freedom for gravitational wave. And when you take the special coordinate system where you have gravitational waves propagating in Z direction, HIJ's components can be written in this H plus and H cross form. You can convince yourself, of course, trace is 0, okay? H plus minus H plus 0 is 0. Good. Then as gravitational waves are propagating in front of you, okay, perpendicular to you, to your line side, gravitational waves are propagating like that. All right, what do they do? So Professor Barish told you how he detected gravitational wave by LIGO experiment. Of course, there's a Virgo experiment in Italy. So you have 2 mirrors, and the laser is coming from the left. You beam split, and when you beam split, you also multiply the beam, wave, you do the phase shift of one of the laser light such that you essentially multiply the electric field of the laser by -1. So then when lasers bounce back in the mirror and come back and recombined, crests and troughs of laser light will cancel. Okay, you have laser light, then you have minus of that. They go away, come back, they cancel, no signal, okay? But when you have gravitational wave, changing the distance between 2 points, crests and troughs of laser lights no longer cancel, and you detect gravitational wave. But, and that's great, right? But you can detect gravitational wave in this way on Earth for wavelengths of about the size of the Earth. Now you do this in space and you have, very long arm, and then maybe you can detect gravitational wave wavelengths of 1 million kilometers or something. But when we talk about gravitational wave wavelengths affecting cosmic microwave background, this stochastic cosmological gravitational wave, their wavelengths is billions of light years. You can't possibly use this to detect gravitational wave billions of light years wavelengths. So we use the universe as a detector. Imagine you have an isotropic radiation field, CMB. Gravitational waves are propagating through it. Then as space is stretched, wavelengths of light is stretched also. If wavelengths of the light is stretched, it's a colder photon. It loses energy, okay? Or it's and then when it comes back, it's squashed, it gains energy. So you have hot and cold, hot, cold pattern around this gravitational wave. If you now put electrons at the center, gravitational waves are coming toward us. Then light is coming from above, gets scattered by electron, and light is coming toward you, okay? Electron sees hot photons above, below. Electron scatters that light into you. And the electron sees cold photons left and right. Electron scatters that light to you. And that light is polarized. Because, daily examples, if you have sunny day, driving the car, sunlight comes from above and then gets scattered by windshield. That light is horizontally polarized. We know that because if you now buy polarized sunglasses that would block horizontally polarized light, but only transmit the vertically polarized light, you can see through the car. Yeah. So, polarization works when you have anisotropic incident light. For example, light only comes from the left, gets scattered, then only one polarization state is picked up, so it's completely polarized. But of course, this is what happens to the sunlight. But universe is isotropic, okay? There's no top, bottom, left, right. There's nothing like that. So then how can you create polarization in the isotropic universe? The answer is locally, electron can see anisotropic radiation pattern. On average, there isn't, universe is homogeneous and isotropic, but locally, because of these fluctuations that you saw already, electron can see hot, cold, hot, cold. So locally, electron can then generate polarization. If you look at, temperature map of the Planck, you see cold, hot, and so on, right? There's a polarization. Yeah, so that's the real data measured by Planck. I was a member of WMAP, but I'm not the member of Planck. So, I just congratulate them for this beautiful, beautiful data sets. Now, how do we make sense of this? So what we do is the following. Let's look at this. You have cold, hot, right? This seems to define plane wave direction. Then let's ask, relative to the plane wave direction, how would polarization direction change? If it's parallel to or perpendicular to the wave number direction, Fourier mode direction, we call this E mode. If it's 45 degree tilted, we call this B mode. And this decomposition is useful because they have distinct parity property. If you flip the spatial coordinates, B mode changes the sign, while E mode does not change the sign. Now, when you then make the power spectrum, you have E square. E is parity even, so E square is also parity even. B mode power spectrum, B is parity odd, but B square is parity even. So this power spectrum of the B mode is still there, even if universe conserves parity. And cross correlation between temperature and E mode is also parity even. But you can also have parity odd combinations like temperature and B mode polarization cross correlated, or E mode and B mode cross correlated. These are not invariant under parity flip. Therefore, they should be zero to within the accuracy of the measurements if universe physics of the cosmology conserve the parity. You can actually then use these correlators to look for new parity violating physics in the universe. That's not the topic of today's colloquium. So let's focus on parity conserving power spectra. There you go. So we had, detection by Corby, 1992, discovery of acoustic oscillations, 2000. Then now it's 2020, we have seven order of magnitude improvement in measurement of the power spectrum. Okay, it's a remarkable progress in the measurements, and we measured temperature anisotropy from the sound waves, E mode polarization from the sound waves. So what you see here is the E mode polarization from the sound waves. When it's gravitationally lensed by the intervening matter, that will be converted into B mode. All of these things shown in red color here is a scalar perturbation. What we're after, which is yet to be discovered, is a tensor perturbation, B mode. Okay. All right. So what happens next? We haven't seen it yet. The first thing that we should note is there's a Moore's laws for experimental noise as a function of ear. Okay, doubling up here now, and future. There's an exponential reduction in noise level because we are working very hard developing better and better superconducting microwave sensors. Then we have, used to be just 10 pixels, then 100, now 1,000, and now 10,000. Now we have tens of thousands of pixels. And future, we have million pixels. And I must tell you that if it weren't for CMB, we wouldn't have this technology today, okay? Because of desire to detect CMB, this technology was developed. And I don't know what else this is useful for, but it gotta be useful for something. No, we have super sensitive microwave sensor, superconducting, and we can just camera, a big camera. So just society has to find a good usage of that, and we can say CMB research is even useful for something in daily life. Okay, now I talked about COBE, WMAP, and then Planck, all satellite missions. We also had lots of ground-based and balloon-borne experiments doing great measurements. Atacama Cosmology Telescope, I told you. South Pole Telescope, I told you. They are upgrading their instruments and they're doing continuing the fantastic measurements. Now we also have the Simons Array in Chile, led by University of California, Berkeley in Japan, and BICEP, Keck Array, that's in the South Pole, that's Harvard, Minnesota, Stanford, and Caltech, and CLASS in Chile, that's Johns Hopkins University. And these are individual efforts, but now we are kind of beginning to wonder whether it makes sense to do it individually or just join the effort. So now we have Simons Observatory, more or less funded, and it's about 10 times more expensive than individual experiment. So we combine, all the experimental efforts. South Pole, Chile, 100 million. If that's not enough, we combine everything in the Earth, and then we have $600 million CMB stage 4. That's ground-based effort. There's a parallel balloon-borne effort, say Spider, led by Princeton. If that's not enough, we launch a satellite. And year 2019, May, we had this wonderful news that JAXA, Japanese Space Agency, approved Lightbird mission. This is the first time that the Japanese Space Agency will do CMB satellite mission. So far we had COBE NASA, WMAP NASA, Planck ESA, now Lightbird, 4th generation satellite funded by JAXA. And we have international partners, NASA, Canadian Space Agency, and Europe. We go to Lagrange 2-point again. Fingers crossed. So let me summarize. We seem to have a very good evidence that we all came from the quantum mechanical fluctuation in the early universe. Inflation seems to do well. Maybe true. The next step, we want to have definitive evidence for inflation by detecting signature of gravitational wave in the B mode polarization. I'm really hoping to find the first evidence from ground-based and balloon within the next 10 years. But then we hope to make definitive measurements using Lightbird in early 2030s. So I stop here. Thank you very much.
Okay. Let me thank Professor Komatsu for this very clear and very interesting colloquium. And unfortunately, we can thank Professor Komatsu only virtually, unfortunately. So it's time for questions from the audience. Just let me remind you that you can actually type your question with the question and answer button that should be on your bottom right on your screen.
There is a raised hand and a question with a raised hand. If you want, I can.
Okay, yes, sure. Maybe you can allow to talk and to ask the question.
Hello, this is Carlo.
Carlo, buonasera.
Hello, Eiichiro. Thank you for this stimulating colloquium. One question that I have is concerning the the unknowns and well, let's say the expected unknowns that we might find in going so deep in sensitivity into an unknown signal, like the curl mode of the polarization. So you have been discussing very extensively the production of perturbations that we expect to be there and produce the signal that would generate the recombination peak, for example. But so we know that big pieces of inflation are still unknown, especially in its coupling with the known forms of energy and particles. So those couplings could lead to unexpected signals in the forms of topological defects, which are known to actually produce all kinds of perturbations, tensors, scalars, vectors, and so appear in the B modes essentially. Which it is a speculative question, I understand, but which likelihood do you assign to the discovery of surprises when we go deep into the primordial signals that you highlighted?
So let's see. I'm not sure if I have actually the plot. Momento. So the question is, right, can we come up with non-gravitational wave B mode polarization? And how can we be sure that we are detecting gravitational wave from the early universe, gravitational wave from the B mode polarization from gravitational wave rather than B mode polarization from something else? And indeed, that's pretty, that's important question, because we don't want to fool ourselves by first announcing the discovery of gravitational wave from the early universe and later say, shit, that wasn't it, it was something else. Equally exciting, but something else that other than the gravitational wave. So for example, Carlo mentioned cosmic defects, but let me actually use something else, okay, as an example. So we can think about, so this is the B mode polarization power spectrum coming from the inflation, okay? So vacuum fluctuation, that's that. A hatched blue is a light bird sensitivity. What's shown in blue is a B mode polarization coming from intergalactic magnetic field, and which we don't know if it exists. So origin of magnetic fields in the universe is unknown. It is a major astrophysical question. It is conceivable that inflation generated primordial magnetic field. And this primordial magnetic field, like Carlo said, can generate scalar, vector, and tensor perturbations. And depending on how this happened in the early universe, you can have this kind of shape of the B mode power spectrum. In that case, it's easy to distinguish this from inflationary gravitational wave signature. But you can also have this red curve from magnetic field, which looks very similar to actually this inflationary thing, okay? Then that's dangerous, okay? So how can we distinguish between them? Luckily, they differ as you go to larger multiples. So if you can then combine ground-based experiments that are sensitive to small scale and then satellite emission like LightBird that are sensitive to larger scale, we can tell the difference. That's one way. Another way, so I told you that we are confident that we see quantum mechanical fluctuations in the scalar mode, because not only the shape of the power spectrum, not only is NS less than 1, but also fluctuations are Gaussian. primordial magnetic field generates B mode that's really non-Gaussian. So if we see non-Gaussianity in the B mode, then we say, okay, maybe that's not quantum mechanically vacuum fluctuation produced gravitational wave. That's something else. So these two are important tests that we must conduct when we see signal. I hope this answered the question, Carlo.
Okay.
Thank you. That was very clear and indicates clearly the necessity of mapping the tensors, the B signal over all the accessible observable scales in the sky. Thank you.
Okay, let me check if there are other questions in the meantime, or if there is someone who actually wants to ask directly to Professor Komatsu one question. Okay, maybe Sarah, you can allow Sabino Matarrese to talk.
Can I?
Yeah, please.
Thank you very much. Hi, Chiro, first of all.
Hi, Sabino.
Since you mentioned this aspect of the Gaussianity of the underlying of the primordial gravitational waves, I remember that in a talk you gave in Leiden some years ago, you gave evidence to this idea of the squeezed states of gravitational waves, which could be another interesting direction to look at. Let me tell you that Nicole and I, the master student of ours, have been recently looked at the quantum to classical transition of gravitational waves, and there is a lot of consequences of this effect. Can you say something about that?
Yeah, amazing. I mean, you are the first person to tell me to remember that I gave this talk in Leiden. Thank you very much for remembering this. Yeah, so for the audience, the question is, okay, we say it's quantum mechanical fluctuation, gravitational wave. That implies gravitons, right? So how can we then say we have gravitons rather than classical gravitational waves? Then this idea, we borrowed from the quantum optics about photon bunching. The question is, when photons come from the source, they come at some intervals, right? And then you ask, is the distribution of arrival time random, a Poisson process, or photons arrive clustered, or photons arrive less clustered? And surprise that people had many years ago was that most of the light sources will give you clustered photons, not Poisson, like you might naively expect. And that generated lots of interesting argument that pretty much gave rise to the quantum optics world. Initial discovery came from astronomers, by the way. And only laser light can give you, coherent light can give you Poisson, give you bunched, and then some weird quantum mechanical signals can give you anti-bunched, like a squeezed light, in particular squeezed way. So then one can ask, can we do the same thing for gravitational waves? And the way astronomers discovered this was to do the interferometry, but not the typical interferometry you might imagine. The typical interferometry is you measure electric fields coming from this direction, electric field coming from that direction, and correlate by time lag. And you see how much time lag do you need to see the correlation. This measures 2-point correlation of electric fields. But instead of doing that, you can also imagine doing intensity interferometry. You have electric field square coming from this direction, intensity square, the electric field square coming from that direction, that's another intensity, correlate. That's 4-point function, okay? So you're looking at something else other than 2-point. So this captures information about photon arrival times and clustering. So then, because we can measure intensity of gravitational wave, using two detectors. In principle, you can correlate the two and see what happens. That was the idea. And then I didn't make much progress afterwards because it seemed like a very difficult thing to do. And Zabino, you asked, what's my thought? I think that's still interesting. I saw a paper by Jiro Soda and Sugumi Kanno on this subject, and they're looking at non-vacuum sources that can potentially give you a gravitational anti-bunching and then see what are consequences. But that's the only thing I can think of it. If you are working on it and have some ideas, I'd love to hear, because I think this is a completely new direction and very exciting to see if that can be measured.
I agree. Thanks, Eiichiro.
Okay, thank you. Let me check if there are other questions. Yes, there is one by Fabio Svirner, so if Sarah can allow him to directly ask the question.
Yeah, can you hear me?
Yes.
Thank you. Thank you very much for your beautiful talk. I'm asking a question as an outsider. You explained us that the discovery of primordial gravitational waves would give definitive evidence for inflation. So my question is there still room for ruling out inflation? And if so, what could be the most plausible way of doing so?
Yeah. I'm not sure, because we have so much data already that confirm basic predictions of inflation that I think if you ask most of physicists working in this area, they're pretty convinced that inflation happened. And then gravitational wave, will give you a definitive answer, but lack of detection wouldn't rule out inflation. Now, if you ask me, actually, in this ideal world, okay, no emission from our Milky Way that will contaminate our measurements. And also, there's no B-mode polarization coming from gravitational lensing. Neither of that exists, okay? Then we must find gravitational wave, because inflation must generate gravitational wave. So if we don't see any gravitational wave signature at all at faintest possible level predicted by inflation, then inflation will be ruled out. Okay, it must be there. I think the unfortunate fact of the life is that our own Milky Way emits bright polarized microwave emission that contaminates B-mode signature, and also this gravitational lensing gives you some level of B-mode signal that will contaminate. So in reality, if we cannot find a gravitational wave signature by the CMB stage 4 ground-based experiment or light bar satellite experiment in mid-2030s, I think we're done. I don't think we can find it from CMB. But maybe, there's a possibility. Let me actually, because I'm very, very optimistic person. Let me actually say that that's not the end of the world entirely, because inflation can predict gravitational waves, not only billions of light years wavelengths, but also pretty much all wavelengths. Therefore, you can use still laser interferometers to detect them. Okay, so even if you don't see light burn, so y-axis is the energy density in gravitational wave, x-axis is the frequency. So this is the LIGO. LIGO is here. LISA, some futuristic ground direct detection experiment. So even if light bird CMB stage 4 wouldn't find it, there may still be a chance that this direct detection experiment will see them. Now, if none of these will see it, that would be a pity, but it wouldn't rule out inflation. So at this point, Yeah, I'm not sure what would rule it out, except we might have a better theoretical idea, some alternative explanation for everything we see. And then they actually predict something new signature that inflation wouldn't predict. Then we find it. Yeah? Then that could be. Now, for example, there's this weird thing that if you look really deep into our data, northern hemisphere of the CMB sky seems to have, which one does it go? Less fluctuation than southern hemisphere. Statistical significance isn't great, but if things like that, right, the point toward massive violation of statistical isotropy, because inflation should isotropize the universe, that may tell you something beyond the inflation. But there are inflation models that predict that as well. So it's, I don't know. I'm sorry that I cannot give you the straight answer. But at this point, so let me summarize, okay? I think the best path would be to find something that's not inflation, that would predict something that inflation wouldn't predict, and find it. Right? That's probably the best way to make progress.
Thank you very much.
Yeah.
Okay, thank you. Let me check if maybe there is there are other questions or some final ones. Okay, here it is. Let me check. Okay, there is one question which maybe you can also read, but anyway, let me just read it for the audience. So there is this question here from Federico Semenzato. May gravitational wave lensing play a useful role in amplifying the signal, hence increasing the chances for direct detectability? Yeah,
thanks for this question. Answer is unfortunately no, and let me tell you why. Let's look at CMB, okay? Before we talk about this stochastic gravitational wave that we're interested in here. So lensing can amplify light of the point source. Okay, so point source, but if you have completely uniform CMB, lensing doesn't do anything. Okay, so lensing conserves intensity of light. The lensing conserves surface brightness. Yeah, so this changes arrival time, arrival directions, but doesn't change the value of temperature. So I think same applies to stochastic gravitational wave background. Because if you suppose that you have a really uniform stochastic noise of the gravitational waves, then lensing would deflect the direction of gravitational wave arrivals. But if it's uniform, it wouldn't really amplify. You see, it doesn't really make it brighter because it's uniform in the sky. This lensing might give you some subtle, higher order effects. For example, lensing produces some higher order correlations in CMB fluctuations that we actually routinely use to map out lensing effect in CMB. Maybe we could conceive something similar for a gravitational wave background, but I don't think this would help detect gravity. I don't think this will help amplify stochastic gravitational wave background. I don't know if Nicola has any further thought because he wrote papers on on propagation.
Indeed, it is something that we are looking at right now. So anyway.
Yeah.
Okay, let me just check if there are other questions. Okay, maybe I can take the opportunity as the chair. Maybe just if there are no other questions, just to make a final one eventually. So you mentioned at some point during your colloquium the possibility of using CMB in order to test actually fundamental physics, and you mentioned, for example, test of parity violation as an extension, actually as signatures of new physics beyond the standard model of particle physics or the standard model of cosmology. So maybe can you maybe just mention a couple of examples in that direction, since you were mentioning this point briefly during your colloquium?
Yes. So let's see. I don't know how many of you actually noticed, but in the advertisement of Colloquium, you saw picture like that, which I didn't show today. So how come is that possible, right? This has to be the figure of the Colloquium topic, but I just sent it because we made it and it looks really nice. So, but you see that photons was coming from this surface of last scattering, and the electric fields are oscillating in that direction. But it is possible that this polarization direction is rotated by physics that violates parity. And one way that can happen is that when you have scalar fields, pseudo-scalar fields, filling space, then you have electromagnetic tensor, kinetic term, usual Maxwell term, but then you have F and Hodge dual of F forming this FF dual that's parity violating. And because theta is a pseudo-scalar field, that's also parity violating, this term altogether is parity even. Now, this term actually makes universe birefringent. So a birefringent material like crystal, you shoot the laser into sapphire, then left and right-handed polarization states acquire different phase velocities. Therefore, when you have one polarization, vertical polarization, let's say, for the incident laser light, went into this sapphire, it rotates. Okay, so, and of course, universe isn't a crystal, but if universe is filled with pseudo-scalar field, then effectively space behaves like a crystal, and CMB photons propagating through it, and the polarization direction will be rotated. Then E mode of polarization can be converted into B in a way that this will produce this TB and EB correlation that can be looked for in the data. And the reason why we made this figure here is that we looked for this in the beautiful CMB at the Planck data sets, and we seem to have found 2.4 sigma signal for this non-zero rotation of polarization. I mean, it's 2.4. You don't have to really take it seriously. But the point here is that this measurement is possible. And certainly with future data sets that I talked about, we can do this better. So not only E and B mode power spectra, we can also look for this parity violating thing to look for new physics. And this new physics is exciting because these axion fields, okay, can be either or both, actually, dark matter and dark energy that we don't know anything about. So if we do detect this coupling, parity violating coupling between dark matter or dark energy field and photons in the form of CMB, because CMB is sensitive, right, to all the fields filling space between here and there. Very sensitive probe indeed. That will tell us a lot about dark sector. So that would be exciting. Yeah. Thanks for asking, Nicola.
Okay, thank you very much. Okay, I don't see any other questions actually, and actually it's 4:20. So I think we can stop here, and let me thank again Professor Komatsu for this really very interesting colloquium, and also for the very interesting discussion that we had after the questions. And okay, let me thank you again on behalf of all the department and the audience virtually. And really, we hope to be able to host you here in person at some point when the situation actually will improve.
Okay, grazie, arrivederci, ciao ciao.
Thank you very much.